Thank you everyone for coming along. Um, um, right, so this is work that I did pretty much following on from my PhD. So I finished my PhD in 2016, and then over the next 5 years or so, I really spent almost all of my research time working with Western disturbances and trying to understand them. And I learned really that there was kind of quite a patchy anecdotal understanding of Western disturbances, and there was really a lot of work to be done. This talk is a review of a lot of the work that I've done in those 5 years and since. But it's not just work that I've done, it's work that my students have done, it's work that my postdocs have done, and it's also work that's come from other groups that I've been involved in. And we really tried to summarize an awful lot here in 45 minutes, but I will try and keep it relatively jargon-free and accessible. This work was largely funded by two projects with the MITRE. We have the MITRE project, which was my fellowship, and then the IMPROVE project, which was my postdoc. So without further delay, let's jump in and talk about Western disturbances. So I imagine when I give this talk, I'm often giving it in Europe or the US, and so I need to explain to people what Western disturbances are here. I don't think that's such a requirement, but I'll give it anyway. So Western disturbances are typically thought of as this winter storm that affects India, particularly the region that I've plotted on this map here. So we've got sort of northwest and northern India, parts of Pakistan and Afghanistan, and then parts of China as well. And you can see here we've got a selection of mountain ranges. You have the Karakorams, the Western Himalaya, and the Hindu Kush. These are the regions that are very sensitive to Western disturbances, but they also impact downstream, right? So you can see all the rivers that originate from the Himalaya here and the Hindu Kush and the Karakoram, and all in the watersheds of those rivers, basically the Indus and the Ganges, there's basically 1 billion people. So 1 billion people are affected just on the water security side of Western disturbances. But they affect a region broader than this as well, right? I mean, if you've been to Delhi in the winter, you'll know that when a Western disturbance comes, you get heavy rainfall perhaps, you certainly get cold weather, and you might get fog associated with it as well. And as we've seen in the last couple of years, Western disturbances are starting to move out of the winter season and start to really interact with the monsoon in a way that's become quite dangerous, and that'll be one of the topics of this talk. So here's a map of basically the rainfall or the precipitation associated with Western disturbances. So here you have the Arabian Sea as the coast here, and then these black lines just show the mountains at different heights. So this is basically the Western Himalaya. And although the heaviest precipitation associated with winter Western disturbances falls along the Himalaya, there is still a reasonable amount that falls in this sort of hill stations and the foothills of the mountains here. And as we know, this is an area where things like rabi crop are grown. So it's really important for not just the water security, but the agriculture as well. And we'll come on to that later. This is what it looks like in terms of the fraction of rainfall or snowfall over the winter months that WDs are responsible for. So this is India here, and then you have Pakistan here, and you can see that there's a region of Pakistan and North India for which Western disturbances are responsible for the vast majority of precipitation that's falling in this region. And you can see the footprint extends all the way down. I mean, when you're out of this yellow area, this is regions that can be affected by WDs. It's far south as Mumbai and as far east as Bangladesh. So it is a very big region that these guys can affect. One of the motivations for looking at Western disturbances is not just the mean state, though, not just these kind of average precipitation, but also the extremes. And here are examples of extreme events that Western disturbances have been involved in. These are synoptic charts, which I shall explain now, that show effectively the kind of the winds and situation around extreme rainfall events that led to serious flooding in North India. We have 3 here in September 1988, September 1992, and June 2013, which many of you will be familiar with. There's probably the only one that's happened in most of your lifetimes. That was the one that caused the Uttarakhand floods. The synoptic situation in 2025 for Tarali, very similar as well, as we'll come to see. But what you have here, in the green, these green barbs, as we call them, show the jet stream. So that's basically the winds high up in the atmosphere. And you can see that in each case, the jet stream has this kind of kink associated with it. that kink is the western disturbance. So these systems exist predominantly at quite a high level, high up in the atmosphere, sort of around 300 hectopascals. So that's basically the height that planes fly at, if you like. And then these purple lines show the vorticities. That's a measure of how much circulation is in the air, if you like. And it shows these kind of elongated shape that western disturbances have. And then typically to the south of these systems is where the heavy rainfall occurs. Now you'll notice these dates are all dates that occur within the summer monsoon. So these heavy rainfall events associated with the western disturbances are all occurring when there's an ample moisture supply for them to work with. And again, we'll get on to why that is particularly dangerous later. So alongside the heavy rainfall, there's other natural hazards associated with western disturbances as well. That's things like cold waves, fog, avalanches and landslides, all these kind of mountain hazards associated with heavy precipitation. And as I say, in the winter, they can be bad news, but if they interact with the summer monsoon, they can be really catastrophic. So these colors here show basically the heavy rainfall, right? You can see these values of over 100 millimeters per day over pretty large regions. And these are pretty large mountainous regions as well, so they're funneled down quite quickly. This is what western disturbances look like over the course of a year. So we start in August in the middle of the monsoon, move through to the winter, and then we go to July. And you can see they have this very pronounced seasonal cycle where they're really peaking during the winter months, and then they're typically very rare in the summer months. And these bars are coloured by western disturbance intensity. So where you have the red bars, that's where you're getting the very strongest storms. Those are the ones that really have an on-the-ground impact. And you can see during the summer months, this is over about the last 70 years, these summer months are really very rarely associated with these strong western disturbances. But that is changing. Whereas in the winter months is when you get these intense ones, but rather than dumping rainfall, they're dumping typically snowfall. So it's not so bad. Now, to understand more about WDs, the most important thing is to get a useful catalogue of them. And that, before my postdoc on this, didn't really exist. So a lot of the studies beforehand were done on really case study events. So people would take individual WDs, they'd look at them in the literature, then they'd draw up synoptic charts of these systems and learn about one specific WD. And that gave us quite a patchy knowledge of them. In the advent of modern meteorology, we have these tools called reanalyses, which allow us basically gridded weather data going back 70 years, which we reconstruct from weather observations, basically combining them with weather models and repeatedly updating the weather models, such that we have a very good idea of what the structure of the atmosphere has looked like over the last, really since the 1980s, they're very good. That's the satellite era. We can go back even further with a bit more uncertainty. Because we have all of this information, we can then track western disturbances in these reanalyses, and that's basically what you're seeing here. So we use that measure of vorticity, that upper level circulation. We identify, that's what we're doing here. We kind of smooth it out to capture the large scale features. We're just looking at the northern hemisphere, and you can see the white colors show areas of very high vorticity. The red circles then show areas where that vorticity is sufficiently high that the system could be identified as a western disturbance. And the green tracks are what those red circles make as you roll it forward in time. If we aggregate all of those tracks and then just take the ones that pass through India, we end up with this panel at the bottom. And this is basically the track of every western disturbance over the last 50 years. We have about 3,000 of them. You can see many of them actually don't really get too near to India, and many of them are quite weak as well. But the average path, this green dotted line, is effectively passing right through North India. And this is the average track of western disturbances. There are many different identification methods as well. This is not the only one. But in my opinion, it's the best one because you can really find these things in the data and then link them together and come up with this catalogue. With this catalogue, we're then able to do a frequentist approach, right? We can take the mean structure of these systems and learn a lot about what they look like. And that's what we do next. So once we have our track catalogue, we do this process called compositing. And compositing allows us to get an idea for what the vertical and horizontal structure of these systems looks like in a way that we haven't been able to do before. When we do this anecdotally with single WDs, all WDs are different, right? So we don't really have a good idea for what the mean structure looks like. But now we can with this reanalysis-based approach. So what I show here is a composite that basically runs through the middle of a western disturbance. So if you imagine taking all western disturbances lining them up by their center, and then stacking weather information, and then taking an average through that stack. That's what we're doing here. So you have basically the whole troposphere going up the side. So this is the surface at 1,000 hectopascals, that's where we live. And we go all the way up to the jet stream at 200. That's what you can see here, because this composite is zonal wind for western disturbances. And you see how the value is very high in the upper troposphere. That's the jet stream, basically. You can see on the advanced side of the western disturbances, there's an acceleration of the jet stream. This arises basically through dynamical processes. That acceleration has some knock-on effects that we'll talk about later that are quite important. So this is zonal wind. We can also look at meridional wind. So that's the north-south component of the wind. This was the east-west component. In the north-south component, we see this cyclonic structure, right? So you have winds coming from the north ahead of the system and winds coming from the south behind the system. That basically is indicative of cyclonic structure. And you can see that that's all really stacked up in the kind of upper parts of the atmosphere. And actually, and you'll know this if you've been through a western disturbance, the winds associated with western disturbances at the surface are usually quite light. There we go, northerly winds. This then is the other dimension of wind. So we've done east-west, we've done north-south. This is up and down. So this is the component of wind that goes up. And you can see ahead of the system, we have this ascent. And then behind the system, we have descent. And that ascent ahead of the system really helps promote convection, helps promote heavy rainfall ahead of the system. And this is one of the reasons why when these guys interact with the monsoon, they can be really bad news. The monsoon is already very moist. It's this highly humid air mass. And you throw something on top of that that's able to lift that humid air into the mid-troposphere. Suddenly you get these really big, deep thunderstorms. Another thing that we can look at is divergence. So this is a measure of whether the wind is kind of spreading or coming together. And you can see here the red colors, that shows convergence. So ahead of the WD, ahead of the system, with these convergent winds, they bring together moisture. So not just ascent lifting it, but we have a system that's able to push the winds together, basically kind of work to squeeze the moisture out. Oh, there we go. I've added it in. I should have had these come up at the same time. And then aloft, that divergence, which helps basically accelerate the jet stream. But basically, what if you have convergence below, that moisture and that moist air goes up, and then it has to spread out, right? Because of the continuity of mass. And it's that continuity of mass that gives us the acceleration. And the other thing that we could look at, for example, I mean, we can do this with hundreds of fields, but for the sake of time, we'll just go through 5. We have temperature. So we have temperature. And one of the things that we notice with WDs straight away is that when we look at the temperature anomaly, it's always really cold. In the lower and mid atmosphere, it's very cold. This is 2 reasons. 1, they're drawing in cold air from the north, and 2, they're associated with very thick cloud structure from that deep convection, and that effectively blocks the sunlight. Right? So we can combine all of this stuff together to come up with these kind of schematic maps. Now, there's a lot of jargon on here. If there's any particular words on here that you don't know, write them down and you can ask me at the end. But basically, we end up with a map that looks like this. Now, there's a lot going on here, but it's through the reanalysis work that we're able to come up with these pictures. Basically, we have this vortical core, this core of high vorticity in the upper troposphere. That's embedded within the subtropical jet. We know that. And downstream from the WD, as we saw, there's this acceleration. We call that a jet streak, and that arises because of that divergent outflow that I was talking about. And that means that we have this deep convection, right? Convergence at the bottom, divergence at the top gives you this very deep convection. That can be associated either with the broad structure of the WD itself, or there's this secondary effect, right? So near the surface, there's these light winds. They're able to push moisture from the Arabian Sea towards the Himalayas and give you this secondary type of ascent. So we have ascent that comes from the system itself, but we also have ascent that arises from pushing moist air directly into the Himalayas. It can't go anywhere but up, right? It has to go up. And when it goes up, you get the same thing. You get these deep thunderstorms. So that's what I've tried to draw here. And as we know, these things typically propagate eastward. They may disintegrate when they hit the Himalayas. They may not. It really depends on the configuration. Then behind the system, what goes up must come down. So we have descent. That descent makes for a very stable atmosphere, a very stable boundary layer. And combined with this cool air coming from the north, we often get this, what we call radiation fog. And so that's why after WD has passed, if you're in Delhi or in the north, like Ludhiana or somewhere like that, you might get this very thick fog that's associated with WDs, another of the hazards. This is what WDs look like kind of in the wider context. And this schematic was drawn by a colleague of mine, Jean-Philippe Baudouin. And so you get the idea that this is a top-down view over the subcontinent and Eurasia. And you get this idea that WDs are kind of pinned in by all of these larger scale dynamic things. So this is the winter setup. The summer setup is a little bit different. But what you have is over the Tibetan Plateau, as always, you have this large anticyclone, this high pressure. That helps to kind of pin the jet to the south. This is the subtropical jet. WDs sit on the top of the jet, basically to the north, because that's the direction that the cyclonic flow must go. And then the jet is also pinned to the west by the high over Siberia and the high over Arabia as well. So in the winter, this is a very stable configuration. The jet is very well locked into place, and WDs, they will spin up somewhere along the jet, roll along the jet, and then impact India and Pakistan. And in the summer, the configuration is slightly different, but basically this is the setup that we have for most months of the year. Now, not only can we look at the mean when we take a reanalysis and a large catalogue of events, but we can also look at the variability. So these show distributions of different characteristics of WDs that we're able to look at for the first time. And what we do here is a split that's often made in the literature between what they call active WDs and feeble WDs, which is a great name. I think feeble just reminds me of someone who's very weak. Active WDs are systems that deposit a large amount of precipitation over the mountains. That's typically the definition that's given of them in the literature, but it varies depending on who you ask. Here we just say those that are in the top quartile of precipitation over the Hindu Kush, Karakoram, Western Himalayas. And those are coloured in yellow in these diagrams. The rest of the WDs, which we call feeble, are coloured in this kind of grey-blue, late grey-blue. So when we split them by precipitation, you get this exponential distribution. That's characteristic of precipitation. And you can see that some values averaged over the HUD domain can be really large. 10 millimeters a day over an area the size of North India is not insignificant volume of water, right? When we look at their peak intensity, so this is a measure of vorticity. You don't have to worry about the units, but basically the higher the value, the stronger the system. And the yellow dashed line basically shows you where the mean of that distribution sits. So active WDs tend to be a bit stronger, maybe about 20% stronger than feeble WDs, but there is a lot of variability in that. The feeble WDs might be stacked towards the lower intensity. You can have some high intensity WDs that are feeble. This is simply because they've got no moisture available to precipitate. They may be too far north. They might be too far away from the Arabian Sea or something like that. Propagation speed, there's not much difference between the active and feeble, but there's a big spread. And what's really interesting is, canonically, we thought about the subtropical jet, that upper level jet stream, carrying these WDs along. That's actually not what happens when you look at the kind of broad system. Look at these speeds. The jet is fast, 60 meters per second. But the mean propagation speed of WDs is actually much slower. It's about 10 meters per second, a fifth or a sixth of the speed of these systems. And so what really happens is the jet is kind of moving past the WD, and you can imagine it kind of pushing it gently along as it goes. What we see with latitude is a big split. So there's the systems that pass, and we'll come on to this later because this has become a very important part of our research. These systems that pass below the Tibetan Plateau and systems that pass north of the Tibetan Plateau. It's these systems that pass below the Tibetan Plateau are the ones that are really, I should say to the south really, rather than below. That implies they're going underneath, doesn't it? These systems that pass to the south of the Tibetan Plateau are the ones that are responsible for impactful weather in India. The ones that pass to the north are not. Even though they can precipitate over the Hindu Kush or the Karakoram, North India is not going to receive much rainfall for systems passing that far north. One of the open questions about WDs is where they get their moisture from. So canonically, before people were able to do this kind of analysis, they assumed that Western disturbances spun up over the Mediterranean Sea. That's here, right? And that makes sense. They're these eastward moving systems. They're quite big. They should originate from far away. And that because that's the body of water they start over, that's where they get their moisture from. But we remember that WDs are really confined to the upper atmosphere. It's cold and thin up there. It's hard to hold a lot of moisture. And that's not when you track the moisture parcels, clearly not where the moisture is coming from. So we do this in two ways. What we do is we take heavy rainfall events associated with Western disturbances, and we take a bit of air above those rainfall events, and then we use the equations of motion to track those parcels of air back in time. We do that thousands of times, hundreds of thousands of times, and then we can aggregate those and see where the parcels have come from. So sure enough, when we look at high altitudes, 5,000 meters, that's about halfway up the troposphere. Yes, actually, many of the moisture parcels do indeed originate from over the Mediterranean, but they're not carrying any moisture. Those parcels have not picked up any moisture. That's what the lower row shows. The lower row showing where the moisture pickup is happening. Even though the parcels may originate from the Mediterranean, they're dry. When we go to the lower levels, this is where we see the big difference. These parcels originating from over the Arabian Sea are picking up a lot of moisture. In the summer monsoon, they're also able to pick up from over India itself. And that's why, when we come onto it, that's why this precipitation over India during the monsoon is so much higher, because the moisture availability is doubled or trebled, if you like. They don't just have to rip it out of the Arabian Sea, it's there when they arrive in India. So let's talk a little bit about the impacts that are not precipitation related. One of them is lightning. Now, when I started working in Indian meteorology 12 years ago, I was really surprised to learn that lightning is the biggest natural hazard cause of death in this country, because there's so many people at work outside, right? And it's big, right? It's like a big winner if you stack them up and rank them. And WDs are associated with lightning for a couple of reasons. So this map comes from a guy, C.K. Unikrishnan, who published in 2021, looking at the main sources of lightning each year. And he identified these 4 regions as being the regions where lightning was the most common. There's box 1 over North India and northern Pakistan, box 2 kind of over Meghalaya, maybe northern Bangladesh, parts of Sikkim and Assam, and then boxes 3 and 4 that are kind of along the Bay of Bengal coast. When he looked at what the synoptic atmosphere was doing during high lightning strike events in each of these boxes, he found that in box 1 over North India, where some of the highest strike rates are, 90% of the time there was a trough at 500 hectopascals, and that's a classic fingerprint for WD. So basically 90% of the time there were heavy lightning flashes over North India. He was able to associate that with a western disturbance. They actually also appear in some of the eastern boxes as well. As much as 20% of flashes over eastern India are associated with the remnants of western disturbances that have passed through. But over there, much more commonly, it's lower level troughs. These are things associated with monsoon depressions, for example, low pressure systems, tropical cyclones, that sort of thing. So, why do western disturbances result in heavy lightning over North India? Well, the answer really lies in the configuration that we have in the pre-monsoon. So, imagine you're in North India in April or May. It's extremely hot, right? It's very, very hot surface. It's been baked by the sun for months. A western disturbance comes along up here somewhere, and it's dragging moisture up from the Arabian Sea. That means you're getting moist air passing over basically a frying pan, right? You imagine throwing water in a frying pan, it just boils. That's exactly what's happening here. That's why we get this streak of high lightning. And then, of course, it's exacerbated as that water then it hits the foothills of the Himalayas and it's forced to rise. And it's made very extreme indeed. Not all impacts of western disturbances are bad, though. And you may be familiar with the Karakoram anomaly. If you're not, what it is basically this idea that because of climate change, glaciers in the world are all reducing in mass. Pretty much everywhere, except for in the Karakoram, where glaciers are stable. That's basically what this color is showing. The color in the arrow is basically showing the glacier health. The bluer the circle, or the bigger the arrow, the better that glacier is effectively doing with climate change. And you can see here in the Karakoram and some parts of the Pamirs, there we're getting the blue colors. If we did this globally, it would be red almost everywhere, right? Because glaciers are melting due to climate change, but not over the Karakoram. And part of the answer to that is that with climate change, western disturbances have been able to pick up more moisture from the Arabian Sea. As you warm the atmosphere, there's this thing called the Clausius-Clapeyron relationship that comes from moist thermodynamics. For every Kelvin or degree Celsius that you warm the atmosphere, it can effectively hold 7% more moisture. That means basically 7% more precipitation. And so we've been able to dump more snow over the regions that they affect. Now, that's offset by various other things in other parts of the Western Himalaya, but this area, which receives almost all of its winter precipitation from WDs, is on the up. And we've also shown this work, well, I say it's in prep. You see how old some of these slides are. This was published last year now, 0 dear. But what we have here is a case study over India, and a colleague of mine at Princeton, Yuanyu Xie, collected all of this air quality data for different cities in northern India and then has aggregated it here. And then these circles show the track of a western disturbance. This is a single case January of 2021, I think. And you can basically see as the Western disturbance passes over, so January 4th, January 5th, then here's the Western disturbance. It's associated with heavy precipitation. That's what these blue bars show. And once it's passed over, and these could be in November, this could be in November, December, or January. Here it's in January. It basically, all of that rainfall is able to clean the air. It's not just the rainfall, it's the winds as well, right? It ventilates these cities. So often in the winter, there's very weak winds over northern India. WDs, they're not associated with very strong winds, but it's enough to ventilate out some of this precipitation, ventilate out some of this pollution. What we showed in this paper that was particularly interesting is that there was this claim that air quality measures in India were the cause of reduced pollution over northern India in the last 10 years. Actually, you can show that almost 75% of that effect comes just from Western disturbance frequency increasing in that period. That actually the weather has been fortuitous and cleaned the air for us. And it's not been policy changes. Well, okay, so it's been policy changes to a small degree, but WDs have done most of the hard work for now. So that segues us nicely into climate, and WDs and climate has been a particularly tricky topic because they exist in this very complicated balance of synoptic powers. They exist across seasons, and they're affecting areas that vary significantly with time. One of the best things we can do to understand WDs in the modern climate is to look at them in the past. And one way to do this is to look at what we call proxies. So you can go up into the Himalayas, you can cut tree rings to learn about the past 500 years. You can go into caves in that area and take what we call speleothems, that's stalactites or stalagmites. And again, you can cut through those as a long cross section and learn about what the seasonal precipitation's been doing in different areas. And by doing that in many places and over many proxies, you can start to reconstruct what the climate looks like in winter or summer, depending on what your choice of proxy is. And what we see is that basically where we have periods in the paleoclimate that we know were warm, so places like the Roman warm period and the medieval warm period, which were also warm over parts of Asia, and also the early Holocene, which we know to be very, very warm. That was about 12,000 to 8,000 years ago. We know from these proxy studies that WDs were much weaker then. They may have, they were either fewer or weaker. And that is something that tends to come out in climate models as well. The tricky part with this is that many of these studies, many of these periods throughout paleoclimate history, there's not really enough studies yet to come to a kind of full consensus. But there's a few periods, like what we call the mid-Holocene, for example, where there's loads and loads of studies because it was a period of abrupt climate transition. And in fact, we think that the transition to this very weak Western disturbance type of winter was one of the reasons the Indus civilization collapsed as it did 4,500 years ago. When we come to the modern day, what we might call the instrumental record, this is really quite a challenging signal to disentangle. What I did here as part of our review paper was basically to go back through every paper in history that had made some measure of WD frequency or intensity, and that's what each of these shows. So down the bottom here we have years, starting in 1950 and coming up to the present, and then each of these up the side is a paper. The paper may look at a different season or a different region, but in each case they're counting something that's to do with Western disturbances, usually their strength or their frequency. And they basically can be summarized into three different methods. That's the observational record. So agencies like the IMD, for example, produce these weather bulletins. In the weather bulletins, they say there has been a Western disturbance on the 8th of March 2021, and someone in the study will put a box in the 8th of March 2021, and then you rack that up over all the bulletins, and you end up with this kind of long observational record. Then we have the feature tracking and reanalyses. That's the method that I showed earlier, where we do it objectively using vorticity. And some studies have used what we would call like meteorological proxies. So looking at things that are sort of slightly related to WD activity, we might take some of the signals that we know they make in the atmosphere and use those as a kind of measure of WD intensity. Anyway, the important thing with this is that you'll notice these minuses and pluses in the top. Where we have a black minus or a black plus, that means the trend is statistically significant. Where we have a grey plus or a grey minus, that means there's a trend that is not statistically significant. And where we don't have a minus or a plus, that means there's no discernible trend at all. Now you can see the disagreement between these studies, right? There are even between the same methods. So even in the observational record, we have a mix of pluses and minuses. In the meteorological proxies, we have a mixture of pluses and minuses. It's an absolute mess. One of the things that we can do, though, is start to break these out. As I mentioned, these studies look at different regions and different seasons. One of the things we were interested in were these reports that there are definitely more western disturbances in the monsoon in the last few years. This is something that was kind of anecdotal in the last 10 years, but we now have the power to look at it. This is what we can show here. So I'll do it from this part first. What we have here is basically the years along the bottom and then the month of the year along the top. So basically what you look at in May, for example, is the number of WDs in May of each year as you go forward. Just look at May and June for a second. You can see it starts in these kind of blue colors. And then as we move to the last 10 or even 5 years, there's a really sudden increase in May western disturbances. You see the same in June as well. And if July wasn't off the bottom of the color bar, you'd see the same there. So you get these big black pluses in all of these pre-monsoon and monsoon months. So there's a very, very clear signal that more WDs are reaching the summer monsoon. And for those reasons I talked about earlier, that's a really bad thing. I think we all know that. The reason we think is because of the heating of the Tibetan Plateau. I showed that configuration earlier where the Tibetan Plateau helps to lock the subtropical jet in place. And that subtropical jet is what's bringing these western disturbances into India. Well, typically in the summer months and in the monsoon months, that subtropical jet moves northwards and takes WDs totally out of contention for India. Now, we think it's staying in place for much longer because of the heating of the plateau. And that's allowing these WDs to attack North India more and more and more often, giving us this increased risk of monsoon interactions. We spent some time figuring out all the different ways in which WDs can interact with the monsoon. And this involved looking at a whole bunch of different cases where the two had come together and created heavy precipitation. What we found was basically that there are 4 different ways they can interact. So you can imagine a western disturbance coming over the top of the monsoon trough. Both of them are cyclonic, right? They're both rotating cyclonically and so you can imagine they're both spinning counterclockwise. They come over the top of each other. The 2 vortices, if you like, then couple together and create a very strong system. Or we can have it such that remember that the jet streak I was talking about earlier, that acceleration of the subtropical jet downstream, that's associated with a region of ascent. That ascent can help lift air up and give you deep convection. Or it can simply be the case that the monsoon and the WD can simply pass moisture to each other. So you end up with moisture in places that it wouldn't be otherwise, resulting in heavy rainfall in places that are not used to it. Now, in 2013 in Uttarakhand, this is exactly what we saw. The monsoon trough provided moisture directly to the western disturbance and resulted in heavy rainfall there. And then right at the end of that interaction, the 2 systems coupled together, basically, and gave us heavy rainfall. There's been a lot of talk about the 2025 monsoon. It's been record-breaking in terms of western disturbances. We've had on average, we have 0 or 1 strong western disturbance per month in the summer monsoon. This year we had, so that would take you to a total of, say, 2 to 4 over a season. This year we had 17, as counted by the IMD. So we're looking at a comfortable record-breaking monsoon. And if we look at all of the heavy rainfall events that occurred in North India during this season, you see exactly the same pattern. A WD is involved in some way in each one of those heavy rainfall events. Typically, so you can see here, right, in the upper levels, these orange or red arrows, that shows the subtropical jet. That shows the subtropical jet. Look how far south it is. This is the monsoon. It should be up over China, but it's not. It's hanging out over North India, and it's generating western disturbances, and each one of those is interacting with the monsoon in such a way that moisture is being driven up towards North India or even northeast India in some cases, and resulting in these very heavy rainfall patterns. And this has been a consistent pattern in 2025. We predicted this. It's now happened. Climate change is happening right now. This can be attributed directly to climate change. What's it look like in the future? Well, aside from this continuing trend into the monsoon, continuing trend of systems into the monsoon, we do know from climate studies, and you'll remember from the paleoclimate where I said where we have warmer atmospheres, we tend to get weaker western disturbances and fewer western disturbances. That's exactly what we find if we look into climate models. So this shows years. This is basically the pattern we have now of western disturbance frequency. And as we run into the future, you see how all of these lines are starting to fall down. These lines represent different climate projections. Now, these are CMIP5 models, so they're a little out of date, but the climate projections basically go from fairly mild climate change over the coming century, fairly extreme climate change over the coming century. What we find is basically that all of them project a decline in frequency of western disturbances over the coming century as a function of climate change. I can answer the question as to why that happens in the Q&A if anyone's interested. But it looks like we're expecting a reduction in frequency of about 15% and intensity of about 12% by the end of the century, pretty much regardless of which projection you choose. There's a bit of spread. You see here, these are footprints of the WD. This is a footprint of its vorticity in the upper levels, basically how strong it is. And you can see we're basically knocking about 10% off as we go to a future climate. This means complicated things for winter precipitation because even though we're getting fewer WDs and they're getting weaker, there's more moisture availability, right? Because the world is getting warmer. We're able to pick up more moisture from the Arabian Sea. So we get these complicated patterns that basically in some areas we're getting more moisture. So over say, the Himalayas and Tibetan Plateau, more precipitation. That's positive. That's blue. Positive precipitation changes. And over much of North India as well. But over parts of Nepal and the Western Himalaya, basically big growing regions, we're seeing a decline in precipitation. This is regions basically where the rabi crop is really dependent on WD rainfall. And we're actually seeing a decline in those regions, but an increase almost everywhere else. And if we zoom in with really high resolution models, we see the same effect, right? You get this red tongue across the foothills of the Himalayas, and then it's dark blue, so much more precipitation to the south and to the north once we get there. And it's also, because of the increase in temperature, has a real effect on the snowfall. So we're often trading snowfall for rainfall. We don't mind if WDs cause heavy snowfall in the winter because it just sits there until the spring. But if WDs come in say, March or February and dump a load of heavy rainfall over a region, obviously that's terrible news for the rabi crop because there's no snowpack to build up. If we dump rainfall, it actually melts the snowpack away. And what we need is that snowpack to exist through the spring so it can feed these crops. Understanding the change in WD precipitation is a complicated task, and it's one we've devoted a lot of time to. Here, what we've done is a process called pseudo-global warming, which sounds a little bit kind of like fake science, but it isn't. What you do is you take a high-resolution weather model. Here is one called WRF, stands for Weather Research and Forecasting. And we run it at a very high resolution, so it's able to capture all of those processes involved with the mountains and convection and all of those things that are tricky to model. And as we initialize the model, we do it for a control period, so we just simulate previous western disturbances as they happen. That's fine, that gives us a control set. Then, over a different set of experiments, we take the same western disturbances, but just tweak the atmosphere to reflect what future climate will look like in sort of 50 or 100 years. And then we can break down moisture flux. So moisture flux is basically the thing that tells you where moisture is moving from these systems and where it's likely to end up. And what we find is that from additions to moisture, so basically because the atmosphere is able to hold more moisture, we get a big increase. We'd expect that. But because western disturbances are getting weaker, we get a decrease. So you get this tug of war, right? This is what you'd expect from the previous couple of slides. It turns out that the moisture wins by about 10%. So over the region as a whole, we expect more precipitation. But because of this complicated dynamical picture, there are some regions, as you can see here, where WDs get much weaker and the moisture flux is actually reduced, and that's what causes this reduction. Well, I'm going to finish by talking about forecasting WDs, which is still in its relative infancy, and I want to show you how hard this problem is, even for the IMD, who are experts in this stuff. I mean, they've been tracking and forecasting WDs for a long time. Here, I've taken 4 previous cases of WDs that have caused a loss of life somewhere in North India, so they've all resulted in casualties. And I've plotted here the warnings issued by the IMD, the Indian Meteorological Department, for the day on which the heaviest rainfall and the casualties were recorded. So day 0 shows you what warning they issued on that day itself. And then this is the day before for the heavy rainfall day. This is 2 days before for the heavy rainfall day. Basically, where you have those red and orange areas, that means you should really be very cautious. But you can see here, for example, in this heavy rainfall in Jammu and Kashmir, it's a red warning on day 0, but that's difficult for people to take action. The day before, it's just a yellow warning. So measuring the impacts in the model turned out to be really, really hard. And actually, as we look down the list, even on day 0 for a couple of these, there were no red warnings because the forecasting the impacts is so difficult. And the reason for this is the models that we use for weather forecasting are quite coarse. They're often 10 or 15 or 25 kilometers grid boxes. Think about all the weather that can happen in 25 kilometers, right? You've got all these complicated mountain and valley structures, all these cloud structures. Because we're not able to represent those explicitly in these weather models, we have to use what are called parameterizations. That's basically statistical approximations to get around this. And that means it's really, really difficult to forecast the rainfall or the precipitation associated with these things. And then it's even harder to forecast the compound hazards that arise from them. So you can see just in these 4 cases how difficult it was for the IMD, who are experts at this, to try and produce a warning forecast that was actionable to population on the ground. We move out to the medium range, so this is now looking at forecasts of WDs maybe 10 days in advance. It gets even harder. So this is work I've done with a guy at IMD where we applied our tracking algorithm to forecasts of WDs, or to forecasts which had WDs in them. And there were 3 in this 10-day period in February 2020. I coloured them in different colours. Now, one of the things that they do is run these models in what are called ensemble modes. So you basically take slightly different initial conditions for your forecast. We rely on the fact that the atmosphere is chaotic, so they diverge from these initial conditions, and you end up with a distribution of forecast states down the line. And you basically end up with all these. You might see this in tropical cyclone tracks, right? If you've ever seen, like, for tropical cyclone forecast, you see this cone, right? That cone gives you an idea of the uncertainty associated with these things. That's kind of what we're doing here, right? That's what these tracks would do. You could imagine these are a cone. Now you can see for the red and yellow systems, the ensemble forecasting system was able to predict fine that they all passed over North India, but with some variation in latitude. But look at this blue track. This blue track landed right in North India, had very, very high impact over North India in February 2020. It was in the first few days of the month. But beforehand, the ensemble forecasting system, and this is only initialized on the 1st of March, so this is only actually 3 days in advance of its impact, is projecting almost half of the tracks. Half of the ensemble members project that the tracks are going to go north of the Tibetan Plateau and have no impact at all if they go north of the Tibetan Plateau, not over North India anyway. So it shows you how difficult this forecasting problem is, not just from a model point of view, but also from this sort of bifurcation point of view, right? We have these almost 2 distinct impact states that exist. And this is something we're really trying to focus on, understanding the processes that lead to the decision the WD makes, if you like, as it gets to the PAMIRs. And as we move out to longer and longer lead times, basically the problem gets even harder. So this is a similar thing where we're trying to create these kind of cones of impact associated with WDs, but now at many weeks in advance. And you can see when we have a forecast here that's initialized basically on the day itself, so it's given sort of 1 or 2 days, it correctly gets that all ensemble members of the WD impact North India. But as we roll it back a week or 2 weeks or 3 weeks, it gets very, very difficult. And so forecasting WD tracks is still hard. You can imagine how difficult forecasting their impacts is when we couple it to these coarse resolution models. One of the things that we can do, I will wrap this up soon because I appreciate I said 45 minutes and I'm now on 50. But I like talking about these things, as you can tell. One of the things we can do is we can correlate WD frequency per month with sea surface temperatures. So one thing that's really helpful about the Earth system is that the sea surface temperatures vary very slowly. Things like ENSO vary over a couple of years, right? And that gives us some predictability that we might know in advance. Is there a season where WDs are going to become more common or more frequent or less frequent or stronger or weaker? So what we've done here is correlate the monthly frequency of western disturbances with sea surface temperature. Where it's red, that means hot sea surface temperatures are typically associated with more WDs, and where it's blue, that means fewer. And what we did basically was find out that ENSO really didn't seem to be a control on frequency at all. So El Nino is often thought of as something that really impacts tropical weather, really impacts the kind of circulation in the tropics. It doesn't, not for WDs at least, and not for WD frequency. But we found these other modes that were hitherto sort of unknown. The NAO, this is the North Atlantic Oscillation. This actually is really important for weather over Europe. But because the subtropical jet originates over the North Atlantic, a lot of its behavior can be explained by the NAO because there's a lot of instability, if you like, over the North Atlantic that controls it. And these other modes as well, what's called the Pacific Decadal Oscillation and the Southern Annular Mode. And we still don't really understand why the Southern Annular Mode pops up when we do this kind of correlation analysis. This is another case for open research. But I did have a PhD student try and understand the connections with El Nino. I wonder just how many slides we got left. Oh, that was the last one. Jolly good. Okay, good. So I won't run over an hour at least. So what we know when we have an El Nino is that we get a lot more precipitation over the Western Himalayan winter. That's what this blue stuff shows, right? But we didn't see any change in Western disturbance frequency. And we know there's not really a change in Western disturbance intensity in El Nino either. So what's going on? Well, my PhD student was able to figure this out with some careful analysis. And she basically showed there's this subtle difference in the latitude of the subtropical jet. Remember that thing that's carrying WDs into the subcontinent? During El Nino years, circulation changes such that the jet is very slightly further north. And that has this impact that it lifts WDs very slightly further north. What that means is they're further away from the Arabian Sea. They're further away from their moisture source. So even though we're getting the same number of WDs and there's the same intensity, they're not as easily able to extract moisture from the Arabian Sea. And that means less heavy, other way around. That means less precipitation during La Nina, more precipitation during El Nino, which we can still attribute to WDs, but it shows the need to be cautious when we're doing this kind of composite analysis. Anyway, one of the things that we came up with at the end of the review was this long list of open questions, and I've kind of posed some of them in this talk, right? Particularly the ones to do with forecasting. There's a lot of jargon in this slide, and that's kind of deliberate to show that these problems are complicated. But there's so much that we still don't understand about these crucial weather systems. We don't know whether WDs occur in clusters. Over the UK, we have these windstorms. They're called extratropical cyclones. We know they occur in clusters because there's a dynamical feedback. We don't know if that's true for WDs. There's still no way to classify WDs. When you hear about tropical cyclones, in India, we talk about cyclonic storms or supercyclonic storms or very severe supercyclonic storms, I think it is. Over the North Atlantic basin, we talk about Category 1, Category 2 hurricanes, something like that. There's nothing like that for WDs. So when the public hears a WD is coming, they don't know what kind of impact that's going to mean, right? What's it mean in terms of precipitation? What's it mean in terms of impact? We don't know. And there's so much stuff we still don't understand about the dynamics. Can they merge or split? Are they associated with fronts? There's lots of stuff that we don't understand about the compound hazards associated with them as well. We still don't really understand what features of WDs lead to cold waves and what drives that cold wave intensity. We still don't know they're linked to avalanches, although we know anecdotally they're related to avalanches. And we still don't really know what kind of costs are associated with their impact on water security. And as I talked about on the teleconnection slide, this link to sea surface temperatures, many teleconnections are known, but we don't understand the mechanisms. Until we understand the mechanisms, we can't trust the models, right? And climate as well. There's still many questions that exist with climate. Certain paleoclimate records really disagree at certain eras. We don't know exactly what role WDs are playing in the Karakoram anomaly and how that's going to change in the future, mostly because climate models can't resolve those processes. And we still don't really know the future of Himalayan precipitation, except for the fact that it's very uncertain. So hopefully I've convinced you that we know a little bit more about WDs than we did 10 years ago, but we still don't know nearly enough. Thank you very much.
So thank you, Kiran, for this very interesting talk. Before I actually open up, to the rest of the audience, I have one question. As you said, it's very hard to predict the Western disturbance, when it's going to arrive. And you have shown this very interesting slide about IMD's, effort to predict a WD and how difficult it was. So, what is considered as like a reliable forecasting or prediction for a WD?
As in what?
Like
what operational?
Yeah. From a personal point of view.
So I think the IMD is still probably the best at forecasting the impacts of WDs and probably among the best in forecasting tracks. Now, there are global models that do probably a slightly better job in terms of tracks. places like ECMWF that we know have basically state-of-the-art global weather models. But I think in terms of the impacts, that IMD is still the best. The problem is the resolution of weather forecast models is still not high enough to forecast these impacts. And so we're basically left at the point where the best weather models we have are still not good enough.
I guess that shows, how complex the overall like there's a science is, right?
Hello, myself Raj.
Hi.
So I'm eager to know that you have explained earlier that the frequency of the western disturbances are impacting the pollution level in India, even better than the policy, right? So in what ways they are impacting the pollution level in India? Could you please elaborate with an example?
Right. So one of the things about pollution is it's basically particulate matter in the air, right? That's suspended in the air. WDs provide two things that help get that particulate matter out of the air. One of them is rainfall. The rainfall comes down, and it literally, you can imagine, so particulate matter is very, very small, usually 2.5 to 10 microns. So you could imagine it's sort of this size. A raindrop is millimeters or beyond, so 1,000 times larger. So it's like this huge water drop coming down and just collecting the pollution as it goes, and then it just takes it to the ground, and then whatever the particulate matter is just becomes dust on the ground, if you like. The other thing is ventilation as well. So they provide these winds that help drive the pollution out of the cities and into, say, more rural environments. But it's the precipitation worldwide that helps reduce pollution levels. And we see that with WDs as well.
I guess, just to add to that, as you showed that, the model projections say that WDs are going to reduce over time, right? So I would, and then, like you have shown how WDs are actually kind of moving towards that monsoon time, right?
Yeah.
So, that finding is most probably a good side of WD on a temporary level, I'm going to say.
Yeah,
correct?
That's exactly it. So this uptick we've seen in the last 10 years in the winter season as well is due to these slowly varying modes that I was talking about, these like
Yes.
SST modes. So things like the Pacific Decadal Oscillation, it is configured in such a way that we're actually getting a slight increase in WDs at the moment. In the long term, due to climate change, we'll expect that to decrease. And so, yes, your pollution problem then gets much worse because you've been banking on the good favor of Mother Earth.
Okay,
basically,
we will act correct our pollution level ourselves. Okay, so I think there's one more question out here.
Hello, it was a wonderful talk.
Thank you.
Firstly, my name is Lavanya. So my question was on the slide where you mentioned that the WD anomaly modeling supposedly reduces for the worst climate scenario, which is the RC 8.5, right? But then the subsequent slides showed that at least it was a gradient slide, right? So the RC 4.5 had like a reduction in the regions where the WD hits in terms of percentage, but then the RC 8.5 had a reduction. No, sorry, I'm so sorry. Sorry, RC 4.5 had a reduction in the regions which had the impact of the WD, whereas the 8.5 had a higher impact.
Was this the precipitation
Yes,
slide?
it was the subsequent slide. So
yeah,
I was just
so
thinking,
even though as I tried to get across, but it's difficult. There's this very complicated mixture of processes going on when you think about climate change and WDs. Actually, we see this with a lot of systems in the tropics, that they get weaker dynamically. So the circulation weakens, but the amount of moisture they have available increases. The same is true for monsoon depressions as well. We expect the same thing. They're going to become, although they'll become more frequent, they become weaker and wetter. Same with WDs. And that has complicated impacts that we don't really understand in terms of where the precipitation actually changes and how it changes. We can make these arguments from a kind of large scale point of view, right? We know what the dynamics look like on the large scale. We know what the precipitation or the moisture budget looks like on the large scale. But what we don't know is how those terms in the equation then interact with local factors like the orography, like the snowpack, like pollution, which actually feeds back into the atmospheric circulation. And so you end up with these very complicated picture that's difficult to understand. So to answer your question, we don't really know why we see that pattern yet. It needs more investigation.
Yeah, we'll take that question first and we'll come to you. So,
Hello, sir. My name
Hello.
is Satyam. My question is related to that you said that WB is responsible for winter precipitation. So you mentioned in the slide that while talking only that rabi crops, it is affected rabi crops. So rabi is responsible for 60% of total food grain production. And recently we have observed that post-harvest losses during 2022 to 2023 due to winter rainfall. So what are your recommendation regarding this event, mainly due to Indian farmers also, maybe, that optimizing sowing pattern or early warning sign, apart from efficient climate modeling, other early warning sign
Yeah,
of
yeah.
Western disturbance?
This is a very difficult question to answer because when we think about when we think about crops, we think about monsoon rainfall and we think about the monsoon onset. Once you get the timing of the monsoon onset right, you've kind of done the hard work, right? You try and plant as close as possible to monsoon onset, and then as long as there's not a break or something, you're usually fine. With WDs, it's kind of different, right? It's a much more complicated thing. It's not a constant source of rainfall, it's intermittent at best. So, to avoid these kind of extreme cases of crop failure, what we really need is a better early warning system so people can irrigate their crops in advance. I think that's the only solution at this point. Changing planting patterns at this point, I think that would rely on data which is too uncertain. We still don't really know or understand what the climate change patterns are going to be for precipitation, except there's probably going to be more monsoon rainfall in the north. But for the winter and spring months, it's still too uncertain. So I think early warning is the way to best adapt to that. And for that, we need high resolution weather models.
Before I come to Sarah, I mean, it's sort of related to that. I believe you said that in 2025 we had 17 Western disturbance events, correct? And on an average, it's 2.
Yeah,
right? Something like that, right? Yeah. So I mean, if you look at or like overall the pattern over the years, is there any other instances where you have seen this much anomaly or even closer to this?
No, it's not a number that we usually keep track of because those seasons tend to be considered quite distinct.
Yeah.
And so WDs in the monsoon is a rare event. So almost like the Earth system, which just kind of burps one out, right? And you get one. But now with the jet consistently in place for so much of the season, I mean, in our paper, we predicted that the jet would stay southward for longer, but then still retreat northwards. What we saw this year for the first time was the jet was there for the whole monsoon. So I don't have an idea on the numbers, but I as far as I'm aware, this is the first time we've seen even over 10 in a season, let alone 17.
It looks quite crazy, right? I mean, yeah.
Yeah. I know this is like, your Don Bradman down to your Virat Kohli kind of levels, right? Twice as much.
Yeah, all right. Over to you, Sarah.
Yeah. So I'm Sarah. And so in your last slide, when you had mentioned some of the uncertainties to do with Western disturbances, I saw socioeconomic impact. So that just made me think about something very similar to the previous question about how communities need to get involved and also be made aware of the consequences, because crop failure is a huge deal for communities that are depending on agriculture for their livelihood. And also, just having them be more resilient and adapt to these disturbances would be something that would be really important in the future.
Yeah. So the question before was a one piece in a 1,000-piece jigsaw puzzle for resilience and adaptation. It's not a question to which there is a single answer. But I think one of the things that would help, so I talked about early warning systems in my answer before, but I think better communication is really needed. People in India really understand the monsoon very well, is what I've found. Whenever I talk to anyone here about the monsoon, they have a very good knowledge of the timing and the kind of rainfall that their town gets and what thunderstorms look like and kind of how they arise. When you talk to people about Western disturbances, it's kind of a bit hazy. They've heard of them. They might know they kind of come from the north or east, but that's sort of it. So when people hear in the news there's a Western disturbance, a lot of people kind of don't really know what that means, except, okay, maybe there's a bit of rain over Delhi or over Punjab or something like that. So I think it's this double-edged thing, right? We need better communications for the systems that we already have, but on top of that, we need to improve the systems as well.
It's quite scary, isn't it? I mean, like something like that. We know something is coming.
Yeah.
I guess we don't quite understand it. then how do we even think about building resilience and think about adaptation rate, right? I mean,
I wish I had a good answer to that question, but I don't think there is one. Really,
Yeah,
I think
yeah.
we just don't know at this point
Yeah.
what the best thing to do. What like I say, it's got to be better prediction of these systems is the first place to start. We can't adapt to them until we know how they're going to change, and we don't know how they're going to change until we have very high resolution climate models. That's a long way off. So in the meantime, what we need to do is basically mitigate, and the best way to mitigate is to get better weather forecast models, which we can run in high resolution. So this year, you may be aware that the IMD launched this 6-kilometer resolution model, the Parat forecasting system. That's a really good step in the right direction, because at 6 kilometers, we can really start to resolve some of those valley features in the Himalayas. And that means we can really explicitly resolve how the winds are interacting with the mountains in a way that we haven't been able to do before. So resolution is one thing. I think ensemble forecasting is another way, because that gives us this good measure of uncertainty.
Yeah.
You could imagine if we had a single forecast that was one of these ensemble members that was going to the north of the Tibetan plateau, but that you're just sampling one state from a broad distribution, this bimodal distribution.
Yeah, totally
And
agree.
the reality is that the track goes to the south, but then you're stuffed, aren't you?
Yep. I think Dhiren has a question. Yeah.
Yes, great talk as usual, Kiran.
Thank you.
I have a related question similar to what people have been talking about. So, I mean, since this is based on the review work you have done, so do you know if there have been efforts in kind of partitioning the internal variability and the climate change signal, especially in light of the recent increase in frequency? Do you know if there are some examples?
There has not been. What we have done is look at specific mechanisms that connect internal variability to WD frequency and intensity, and kind of quantified that in terms of interannual and interdecadal variance, not related to the climate trend. No. So this is again another open question, really. How big is the climate signal? And this may be one of the reasons that we see such variability when we look at historic trends. Because the internal variability has been very large over the last 30 years, that it might be swamping the climate signal.
And the second part of the question is, we already saw that in a warmer climate, we are going to have, let's say, lesser number of WDs, right? That is one part. But I mean, if you happen to trust the current generation of GCMs, be it CMIP 5 or CMIP 6, or let's say even RCMs, right? I mean, where we had, let's say, the historical period up to 2005, if we just create a boundary there.
Yeah.
And if we had this 20-year period where we can actually match what has been happening, although this period will be very small in order to just see, again, the internal variability or the climate change signal. But do you think that whether there is any consistency between this 20-year period, 2005 to, let's say, 2025, with any of the RCPs which we tend to believe?
It doesn't look like it, no.
Okay.
I think we've seen in the last 20 years a general increase in all WDs across the
Which
season.
is contradicting
so not just
to
the summer, not just the summer monsoon where we expect that as a climate change signal, but also the winter and pre-monsoon where we don't so much expect that as a climate change signal.
Okay, great. That's it. Thank you.
Thanks.
Thank you for the talk. Very interesting topic. I don't have a background in climate or geography, but first time I heard of Western disturbance was 10 years ago. I belong to a state called Maharashtra.
Yeah.
So as in one of your slides, you have
kind
mentioned,
of in the fringe area of impacts.
yeah, right. So in 2014 and 15, there was unprecedented hailstorms.
Yes.
So that's when I heard of this. So is there anything you can talk about? What is the reason of this is coming down in the southern regions?
Sure. So there's, as you saw on my slide with the distributions, there's a big distribution in quite a broad distribution in the latitudes. Now, most of them run across North India. Every now and again, you get a track that runs sort of weirdly far south. They can disconnect from the subtropical jet through dynamical processes that we actually do understand quite well. And then you essentially have this detached upper level low that then is acting kind of on its own thing. So it just meanders around until it dissipates. That's what we see in the Mumbai case where we had the heavy hailstorms. And in that case, because I think the areas that got the heaviest hail were sort of on the coastal side of the Western Ghats. So you have the same orographic effect, right, where the WD was driving moisture into the hills. You get this big convection as a result because it's got nowhere else to go. And that's where the heavy hail comes from. Those are very rare cases. And we have other cases as well where hailstorms have devastated crops in regions of North and Central India. I think that there's been cases even on the eastern coast as well, and as far as east as Bangladesh too. So yeah, but they are rare. I mean, but it's still worth talking about because if they can happen once, they can happen again.
I am Harsh.
Hi.
So you were talking about that western disturbances when merged with the monsoons, southwest monsoon,
Yeah.
then in the Himalayan region they create devastating effects, may create devastating effects. So what we are seeing nowadays that Shimla floods and the Dharali, which
Yeah.
with the latest one which have. So can this may be connected with the western disturbances, may be connected with the south?
Oh
west
yeah,
monsoon?
absolutely, absolutely. I mean, this is exactly the climate change signal that we expected to emerge, and this year it did in extreme force, or as we have said in our forecast meetings, with extreme prejudice. Yeah, these events in North India, Shimla, the hill stations, almost invariably, when you get a heavy rainfall event in a hill station or somewhere along the foothills of the Himalayas, even in the monsoon, it's because there's a western disturbance hanging around. We almost kind of have this bet on in our operational forecast meetings. If we hear about a heavy rainfall event that's happened, we haven't predicted, and then we look at the large scale sitting right over the top of the region, there's a western disturbance 90% of the time.
I have one more question that
Sure.
as you told that there is a lack of high resolution data, and
Yes.
as a climate change student, we all face challenges while dealing with the groundwater data or the climate data sets. So, can you suggest some of the data sets to which are high resolution data sets to look into this type of
Yeah,
context?
so there's a distinction to be made here between reanalyses, which are quite coarse resolution, but they're very well constrained by observations. So they basically, we run weather models in the past, but then we kind of pump them full of observations and constrain them to those observations using a process called data assimilation that makes sure the model is in a physically consistent state, but one that is consistent with observations that we know. So it's radiosondes and weather balloons, that sort of thing. So we have a good idea of the vertical structure of the atmosphere. For reanalyses in capturing western disturbances and their structure, we think that 25 kilometers is enough to catch most of the impact. It's probably not good enough for the precipitation because that's still coming out of the model. The model still has these biases associated with imperfect representation of convection, imperfect representation of orographic processes. But there are observational data sets we can use to really probe that. Things like satellite rainfall data sets. There's gauge-based data sets that the IMD produce as well, so they grid the rainfall gauge data. Those are not good in the Himalayas because they don't have very many gauges up there because they're hard to put, and also because rainfall variability is so strong up there because of all the different valleys and mountains. So satellite data seems to be probably the best option when we're looking at historical events. For future events, we still don't really have a good option except for probably downscaling climate data. You might find a WD in climate output from a vorticity-based method that maybe looks like it's got some high impact in the climate model. Then you'd have to dynamically downscale it to see what the answer really was. That's really hard. That's a very expensive task. It's getting a little better with AI, but AI doesn't have a truth for these extreme events, right? So even then, how much can we trust it? Yeah, it's still kind of pretty woolly, no?
All right, I think we have another question out here.
I have a question. You had a slide about paleoclimate.
Can you lift the mic up?
Sorry. You had a slide about paleoclimate
Yeah.
about it, and I'm just wondering that I know that there is dendrochronology where they use tree rings to
Yes.
reconstruct past climate. But your slide also mentioned that there were a lot of disagreements. So, what were mainly the limitations that come up with
Yeah,
this
so
kind of analysis?
I'm not 100% sure why those disagreements arise. Typically, proxies are taken from different locations. And as we saw in future climate studies, there's quite a lot of variability in those trends, even when we have quite a strong warm forcing climate change. You got that tripole, right? The wet, dry, wet. You could imagine that you have tree rings that are kind of sitting somewhere in that dry region or maybe to the north of it. The nature of that tripole could change in different paleoclimate setups. And I think that's probably one of the big sources of uncertainty. Certainly in the tree ring record, that just year on year we're getting, and there's a lot of internal variability as well, what Dhirendra referred to as internal variability, which is this relationship to El Nino, for example, or the Pacific Decadal Oscillation. But I don't have a good answer mechanistically for why there's a disagreement. It's just that all of annoyingly, all of these tree rings tend to sit in the region that's got the biggest uncertainty associated with climate change and paleoclimate because they come together. So yeah, it sucks basically.
All right, and there is another question out here, Lucas.
So thank you for it's a very detailed talk which you presented, and I see from the correlations that you draw from this. What I could see is the Silk Road development perspective. The area which you projected are Mediterranean region, where on the upper north, northern hemisphere, and also it is impacting lower lands regions of the Indian subcontinent. So, what is the correlation between the energy demand? For example, what you showed the areas which we saw are also oil extracting zones which I could see closely, and future demands also which you showed it will be much more worsen in the raining pattern. Is there a correlation between energy demand and the extraction process and the industrialization in these belt? I would say, is there any relationship?
Not sure I understand the question.
Maybe what I can do, I can ask another question to supplement that.
Okay.
Right. So you started with the presentation with the western disturbances and winter precipitation and the water security.
Yes.
All right. So now it'll probably connect, Lucas. You
Okay.
can have this conversation in your postdoc. So now my question to you is, when we know that things are changing when it comes to western disturbance, we know very little about it. Then from 2025, as you have said, is huge anomaly. In the broader perspective of climate change, what your assessment is, contribution of western disturbances into the overall water security or the overall climate security of the region? Like any assessment, even you're able to.
We know that they're very important for water security at both the kind of head regions of the Indus and the Ganges basins. But we don't really know how that security is going to change. This is kind of the point, right? The signal is just so uncertain. We know there's probably going to be more moisture in the region, but then it's being pushed forward in unusual ways. So if it was just more snow, it kind of wouldn't be much of an issue.
Right.
But because you're replacing the snow with these heavy rainfall events, that's generally bad news.
It's not really winter precipitation, right? It's basically precipitation in that winter fringe, right?
Yeah.
And where this seems to be actually, it's kind of getting into.
So we don't know, but for March, April, May, we're not really sure what the signal is for precipitation. My feeling is it's going to, when you look at the winter signal, there's an increase. When you look at the monsoon signal, there's an increase. I'd be very surprised if that was not the case in the spring months as well.
Yeah. Hello, good evening. In your, in the very beginning, you had mentioned that maybe this could have been a reason of how the Indus Valley could have come to an end.
Oh, yes.
If you could throw a little bit of light on that. And secondly, your data sampling, the vertical heights are it's a very wide bandwidth. So if you could throw light on how the terrain would have an effect on the western disturbances in that particular section of measurement.
Okay, so the first question is on. So with the Indus Valley civilization's collapse, this happened during a period called what we call the Mid-Holocene, right? This is about 6,000 years ago, and what models and paleoclimate tells us is basically that western disturbances became so weak during that period, and the monsoon expanded so much that it changed most of that area from a winter and spring growing season to a summer growing season, summer monsoon growing season. So effectively, the agricultural methods they developed no longer worked in the climate they existed in. This is, of course, just a theory. I mean, no one was around. No one knows because there's not a written history or an oral history. But it looks like that might be one of the causes. And you can see this in sort of things like the pollen grain records for the crops that they would have been growing at the time. There's an abrupt cutoff kind of in the Mid-Holocene, whereas civilizations in Central and South India continued because they were summer growing seasons anyway, or monsoon growing seasons. Your second question was it on the vertical structure of the composites? Was that? So in those composites I showed but didn't say where the reanalysis. So reanalysis gives you data all the way to 1,000 hectopascals all the time, whether or not it's real, right? Because often that's below, like you say, high terrain might be below the surface. So in those composites, we remove those cases where or from the sample. We basically put them as like nans, right? So that when we take the average, we're only averaging over real above the surface cases. But these reanalyses have very high vertical resolution. Just in those composites I showed you, there's 37 vertical levels. So it's well sampled throughout. Even.
Yeah, hi.
Hi.
So consider me as someone with very little knowledge of Western disturbances. And this is just something which you said, which is that the particulate matter from pollution, does that affect Western disturbances? And is that something which is included during modeling?
Right.
Or?
This is a really good question, and one that's still a bit of an open question. So we obviously know that WDs can rain out pollution, but we also know from history that aerosols in the atmosphere can really change the configuration, the thermodynamic configuration of the atmosphere. So for a long time, we thought climate change was making the monsoon weaker. What was actually happening was that aerosols were dimming the atmosphere and making the monsoon weaker. Once aerosol policies changed, that we removed them from the atmosphere, greenhouse gases started winning, and the monsoon then took off. So we know that effectively what it is it changes the energy balance from radiation from the sun and the surface. We don't know how that affects Western disturbances yet, but there's a very reasonable assumption that it does. This is taken into account in models. They do have an aerosol component. That aerosol component is radiatively active, so it does include them, and it includes them in the future climates as well. So we have different projections of what aerosol forcing will look like, but we don't know what the mechanism looks like, and we don't know how strong that contribution is. We actually have the data to figure it out. Just we don't have the manpower to figure it out.
It seems to be a very exciting area, and it's an evolving area. And we have quite a few young people, in the audience.
Yes.
So, what would be some of your advice if someone wants to get in there? Some of the areas that they can look at, and what would be your advice as an expert?
I would say, and this is not shameless self-advertising, but go and read the review paper, because that contains the sum knowledge of everything we know about Western disturbances and all the things that we don't know, or that we think we don't know. There's probably some unknown unknowns in there, to quote Donald Rumsfeld, but that would be my place to start. And I know that's where a lot of students who want to work in WDs will start, is with it. You just put my name and review Western disturbances into Google, you'll find it. It'll be the first hit. And then email me if you have any questions about what you read. That would be like I say, not to self-publicize. I don't get profit from you reading the paper, but I think that's
absolutely, yeah, great.
It's not a book I have to sell. It's free. It's all freely available online. All the WD data sets as well. Everything I've shown is freely available online. You can go and do this analysis yourself. Just get in touch if you want to know where it is or you want to know how to use it. Send me an email. I'm always happy to work with people interested in WDs.
Fantastic. Thank you so much. Thank you very much for this very interesting talk.